Okay, let's take a look at some features for worksheet 3. Here we have an equation for heating or thermal energy exchange based on mass, specific heat and temperature. But then we have two additional equations for heating, and these are just based on mass. Remember, when there's no change in temperature is when the substance is changing phase. So heat of fusion represents melting or freezing, whereas heat of vaporization represents evaporating or condensing. And so calculations for that part are actually simpler because they only have the mass and no change in temperature. So these are the values that we'll use. Let's take a look at a sample problem together. So it says a cup of water cools from one temperature down to a second temperature. How much energy does it release? So there's three things that I want you to do. The first is work on this heating curve. And remember, it says time on this axis, but it is really energy added over time. Don't forget. And the second thing I want you to do is make some energy bar charts to represent it. And the third thing is to calculate the Q value to represent the scenario. So let's look at this one. A cup of water cools from 75 degrees Celsius. So I said place an X on the portion of the curve that represents the initial conditions. So 75 degrees Celsius, where is that on this graph? Somewhere around here, right? 75. That's the initial conditions. And then I said place an O where the final conditions are. So the final conditions are 20 degrees Celsius. So I'll put an O right here around 20 degrees Celsius. Then I asked you to highlight, but you can just use a pencil, that would be fine, from the beginning to the end of your graph. And go ahead and put an arrowhead on it too, just to show that, hey, this thing is cooling down. It's going backwards this time across the heating curve. It is not heating, gaining thermal energy. It's losing thermal energy, cooling, right? So that is all I want you to do on the graph, is just represent the change. Here on the energy bar chart, it says to use one to show the phase change and the other for temperature. So did this problem include a phase change? No, water goes from 75 to 20. It doesn't change phase. So how can we show no change in phase? We would use a phase starting number and keep that number the same. That's how we would show no change in the water. That's our system. And no energy added or left the system that contributes to the phase change. We'll use the bottom set to represent temperature. So the temperature started at 75. So let's add some bars under thermal energy to represent that original temperature. And then the temperature went down to 20. And so, 25 is about a third of 75. So I'll just use the 3-bar to 1-bar ratio. And the system is the water again. And does it look like energy entered or left the system? Well, again, we're showing another way to show that these 2 bars of energy left. So that's all for that, because we are separating the phase on the first graph and the temperature on the second graph. There's nothing that needs to be repeated. The last section, section 3, is to calculate the Q, the amount of heat or thermal energy transferred, right? So that is equal to mc delta T, the mass that was given. You see it? The specific heat for water, that's given up above. And the change in temperature. So let me see. It's 20 is the final, and 75 is the original. So we typically do the final minus the original. Now let's plug that in. And it looks like I get a negative number, 32,186. And let's check the units as well. So grams does cancel, degrees Celsius does cancel, and I'm left with joules. But why is it a negative number? Energy cannot be destroyed, but energy is leaving the system. So a negative number means this is how much energy is lost from a water. I'm not asking you to write that word part into the answer. I'm just emphasizing that is why the number is negative. So go ahead and try the other ones.